think so. I think I broke my streak of like.
Well, you were on time today.
Exactly, that's what I'm saying. But I've been like a minute or two late.
Okay, sometimes last year's seniors beat Josh here. Is that bad?
All right.
Dude, why that take so long?
Last year's seniors beat Josh here.
Next year's seniors
They
beat
don't.
Josh here.
So first order linear ordinary differential equation is one that we can write a sub 1 x dy dx plus a sub 0 of x y equals some g of x. That would be a first order linear differential equation. All of our coefficients are functions of x only and first derivative only. In standard form, we can write this as dy dx equals p of x, sorry, plus p of xy equals f of x. And we would get to standard form just by dividing everything by this a sub 1 of x. This is our standard form of a first order linear differential equation. And I just want to note quickly that some of these are separable. So for example, dy dx equals x squared y, or sorry, plus x squared y equals 0 is separable. We can get all the x's together and all the y's together. Or we could also write it as dy dx equals some function of x times some function of y. But dy dx plus x squared y equals 1 is not separable. But this would still be a first order linear ordinary differential equation, the second one there. So our solution method, what we do to solve this thing is we look at the left-hand side of this equation and we say, well, that kind of looks like the derivative of a product. We have y times some function plus the derivative of y times nothing there. In this original way we wrote this, we have y times some function plus the derivative of y times some function. That kind of looks like the derivative of a product. The derivative of first times the second plus the second times the derivative of the first. So our goal, our solution method, is to transform the left-hand side into the derivative of a product. And if we integrate a derivative, we know that we just get the function itself. So we can integrate the left-hand side and integrate the right-hand side and get our solution. So we turn it into the derivative of a product by multiplying by what we call an integrating factor. We want to find some function that we can multiply the equation by that will turn the left-hand side into the derivative of a product. That will allow us to integrate both sides. That's why it's called an integrating factor. Well, the integrating factor is easy to find. So let's take a look at how we do it. We call the integrating factor mu of x. So we need the derivative with respect to x of mu of x times y, which equals mu dy dx plus d mu dx y. We need that to equal the left-hand side of the equation. We need this to equal, if we multiply by mu dy dx plus mu p of x y, and this quantity is our left-hand side. Multiplied by mu of x. That's the left-hand side of that first order linear ordinary differential equation multiplied by mu of x. Well, these two terms are the same, so we need these two terms to be the same. So that means d mu dx has to equal mu times p of x, because we need these terms to be the same in order for these to be equal. Well, this is separable. I can say the integral of d mu over mu equals the integral of p of x dx. And this is the integral of d mu over mu is natural log of mu absolute value of mu of x, and that equals the integral of p of x dx. And we exponentiate both sides, rewrite in exponential form. So mu of x equals, and we get a constant of integration here. When we raise e to that power, we get e to the integral of p of x dx plus c. Well, then that turns into e to the c times e to the integral of p of x dx, so we get a constant times e to the integral of p of x dx. And this constant doesn't matter because we're multiplying everything on both sides of the equation by this factor. So we have c2 times every term of on each side of the equation, so we could divide everything through by c2. So we don't have to worry about that constant of integration to find our integrating factor. And so our integrating factor is mu of x equals e to the integral of p of x dx. If we multiply both sides of everything, multiply through by this integrating factor, we turn the left-hand side of our first order linear ordinary differential equation, written in standard form, into the derivative of a product. That allows us to solve that differential equation by integrating both sides. All right, so this is our integrating factor. So let's look at the process. How are we going to apply this? Questions on how we came up with the integrating factor. It's not super complicated thing. All right, so an example. Y prime plus 2xy equals x to the third. So our first step always is to write our equation in standard form. In standard form, we have y prime with no coefficient plus some function of x times y equals some function of x. So in this case, p of x is 2x, and f of x is x to the third. So my first step is to find mu of x. Well, we know that mu of x equals e to the integral of p of x dx, which is e to the integral of 2x dx, which is e to the x squared. And I don't need to worry about that constant of integration because we're multiplying through everything on both sides of the equation by this integrating factor, and that constant would just be a constant term in front of the same constant term in front of each term, and we could divide through by that. My next step, multiply by mu of x. So I get e to the x squared y prime plus 2x e to the x squared y equals e to the x squared times x to the third. Our next step is to write the left-hand side as the derivative of a product. Well, I can rewrite this as e to the x squared y prime. Because when I use the product rule on this, I get the left-hand side of the equation. E to the x squared y prime equals e to the x squared x to the third. Now we integrate. When we integrate e to the x squared y prime, we get e to the x squared y equals the integral of x to the third e to the x squared dx. Well, this is going to be an integration by parts, x to the third e to the x squared. That's similar to the one we did yesterday for an integral of the day. So e to the x squared y equals, when we integrate this, I get 1/2 e to the x squared minus 1/2 e to the x squared plus c. I need to explicitly account for that constant of integration. This time we have to include that constant of integration. And now I solve for y. So I'm just going to say write the solution. Y equals, I'm dividing everything by e to the x squared. So I get x squared over 2. X squared is divided out there. Minus 1/2 plus c e to the minus x squared. This is why we have to explicitly account for the constant of integration, because when we divide through by our integrating factor, it gets multiplied by that constant of integration. So it becomes part of the solution. Yes?
Why is it negative x squared on the constant?
Because I'm dividing by e to the x squared.
Oh.
So I could write it as c over e to the x squared, which is the same as c to the negative x squared. We call the c e to the negative x squared term is the transient term. Because c e to the negative x squared approaches 0 as x approaches infinity. So it eventually goes away. We call it the transient term. Yes?
Is there any way to solve for p of x, or are we just going to have to be
That'll be that when we have the equation. That will be the equation will tell us what p of x is. So when we have this tells us p of x is 2x. It's just whatever is in front of the y term, the first the non-derivative portion of the equation. And this is the unique solution. Our solution is unique. If we have y prime plus p of x y equals f of x, I can write that as y prime equals f of xy, where f of xy is f of x minus p of x y. Well, if f of x and p of x are continuous, and df, the partial of f with respect to y here, is just negative p of x. So if f of x and p of x are continuous, then our differential equation satisfies the conditions for having a unique solution. All right, we're supposed to get new computers. I really hope my new computer they'll let me install all this stuff on the new computer, and it's much faster. We're supposed to get them this spring.
So like next fall?
Yeah, they're giving us the option not to have a Chromebook, I think.
Oh, really?
Yes, because this computer, I think, is over 10 years old. And so the battery will keep it running on when I hibernate it for about 1 minute. So I have to go from here to my office to plug it in less than a minute. Otherwise, it shuts down and I have to restart it. All right. So our solution that we found is unique because our differential equation, the right-hand side satisfies our conditions for having a unique solution. All right, so let's look at another example. X dy dx plus 3y equals 3. Our first step is to write this in standard form. So I'm going to divide by x, and I'm going to write it as y prime instead of dy dx. Y prime plus 3 over x, y equals 3 over x. So p of x is 3 over x. So find the integrating factor. Mu of x equals e to the integral of 3 over x dx, which is e to the 3 natural log absolute value of x, which I'm going to rewrite as e to the natural log absolute value of x to the third, writing or using properties of logarithms, and I'm going to say that is x to the third. And I can drop the absolute value because we are multiplying everything on both sides of the equation, of our original equation, by this integrating factor. If it is positive, that doesn't change anything. If it's negative, we're multiplying everything by a negative. So we could just divide through by -1 and get the same solution. So we can drop the absolute value. So we multiply both sides of the equation, both sides of this equation, by our integrating factor. X cubed y prime plus 3x squared y equals 3x squared. Rewrite the left-hand side as a derivative of a product. X cubed y prime equals 3x squared. Oh, sorry. No, x cubed y. Yeah. Yeah, so when we take the derivative, we can always check by just taking the derivative of this. So derivative first, 3x squared times y plus y prime times the first. Yes. Yeah. Yeah. The P of X is how we found this. We integrate. So x cubed y equals the integral of 3x squared dx. So x cubed y equals x cubed plus c, and y equals 1 plus c over x cubed. And we have our general solution. Yes?
Is the transient term, is that always the first 0 approach something?
If it has a transient term, the transient term is a term that approaches 0 as x approaches infinity.
Because you're dividing by some
Yeah.
x, and this is
So yeah, so here, the c over x to the third would be a transient term because as x approaches infinity, that term approaches 0. The entire solution is transient. All right, I want to look at one more, this time an initial value problem, and we'll talk about the interval of solution. X times x plus 1 dy dx plus xy equals 1, and we have y of e equals 1. We're going to rewrite in standard form y prime plus 1 over x plus 1 y equals 1 over x times x plus 1. P of x is 1 over x plus 1. So mu of x, our integrating factor, is e to the integral of dx over x plus 1. Which is e to the natural log, absolute value of x plus 1, which is just x plus 1. And we can drop the absolute value because we're multiplying through both everything in the equation by this factor, so it doesn't matter if it's positive or negative. All right, multiply through by the integrating factor. So we get x plus 1 y prime plus y equals 1 over x. Now, I will say that you don't always get really nice quantities on the right-hand side that you end up having to integrate. So just be aware of that. We rewrite the left-hand side as a derivative of a product. X plus 1 y prime equals 1 over x. We integrate both sides. X plus 1 y equals the integral of dx over x. So x plus 1 y is natural log of x plus c. And I'm going to keep the absolute value here because this is part of our solution. And then we can write our solution. Y equals the natural log of absolute value of x over x plus 1 plus c over x plus 1. And now we're going to apply our initial condition. So at, what is our point? E1. At the point E1, we have 1 equals 1 over e plus 1. Natural log of e is 1. 1 over e plus 1 plus c over e plus 1. So that's 1 plus c over 1 plus e. And that equals 1. So c equals e. Don't tell that to your LA teacher. C equals e. In math today, we learned that c equals e.
I mean, if you really read these blocks, you can all think the same way.
Yeah, they do. All right, our solution, finally. Our specific solution, y equals natural log of x over x plus 1 plus e over x plus 1. Why did I drop the absolute value this time? Where's our solution? Our solution is for x greater than 1. So our interval is 0 to infinity. Yes?
If the solution was x less than 1, would you be natural log negative x or negative natural log x?
If it would,
Like, because we're dropping the absolute value of ours because our solution is positive, right?
right, so we don't have to worry about making it positive.
But what if our solution is negative?
You'd keep the absolute value because you can't take the natural, you don't want to take the natural log of a negative. But then the denominators could be negative. I would say, I'm also going to say before I write the assignment, any questions? It's a pretty mechanical procedure. Works pretty nicely as long as the integration is nice. I would say, I'm also going to tell you to look at pages 60 through 62, because our text talks about piecewise differential equations, solving piecewise differential equations, and the error function. I'm not going to emphasize either of those for us, but you can look, they do an example of solving a piecewise differential equation, and a solution that involves the error function. So it'd be nice to read about the error function because not for us so much, but in the future, if you're going into science and engineering, the error function integral comes up pretty frequently. All right, so my T-shirt. Let me show you a picture. Is it? I have to remember which folder it's in. No, I've had this one for a long time. We used to teach. I taught first order linear differential equations in Calc 2 when I taught the Calc 2-3 class. We did 2 days on differential equations. So the title is Smarter Than the Average Bear. Are you familiar with Yogi and Boo Boo? So this is Yogi teaching Boo Boo to solve differential equations. So we have a linear first order differential equation, finds the integrating factor, writes the left hand side as the derivative of product, and integrates to find the solution. So that's what we're going to teach. Yogi is teaching Boo Boo to solve differential equations, so they don't have to steal picnic baskets.
Where did you get out from?
I